Today, we're diving into the invisible nervous systems that run our modern world. I'm talking about everything from power grids to massive factories. Let's get into it.
So, just stop and think about that for a second. How does a giant power plant or a sprawling chemical factory actually work? We're talking thousands of sensors, valves, and motors that all have to operate in perfect harmony, non-stop. How on earth is that even possible?
Well, the answer is this incredible hidden nervous system. And it wasn't just invented overnight. No, this is a technology that has been evolving for decades, getting smarter, faster, and way more resilient with every new generation. So today, we're going to trace that entire journey.
Okay, so before an engineer even thinks about touching a single wire, they have to make a really fundamental choice. They have to decide how they're going to solve the control puzzle. And it really all boils down to two completely different design philosophies. And this comparison really gets to the heart of it. You see, on one hand, you've got the traditional approach. Think of it like a master craftsman at work. You're using experience, proven patterns, and a bit of trial and error to get things just right. This works great for simplest systems. But on the other hand, you have the modern approach, which is built for today's super complex factories. This method uses pure mathematics to design a perfectly optimized and stable system right from the get-go. So the very first big attempt to bring computers onto the factory floor was a totally revolutionary idea back in the 1960s. The whole concept was built around one single, all-powerful central brain. This system was called Direct Digital Control, or DDC. And the idea was pretty simple, really. Every single sensor measuring temperature or pressure and every single motor or valve, everything was wired directly into one giant central computer. That one machine was in charge of the whole show. But the problems with this one-brain approach became obvious really, really fast. For starters, it created a massive single point of failure. If that main computer crashed, the entire factory just stopped, dead. And beyond that, the wiring was an absolute nightmare. Programming it was unbelievably complex, and if something went wrong, man, good luck finding the fault. It was pretty clear this wasn't the final answer. So that single-brain approach just wasn't going to cut it. The solution was to ask a totally different question. Instead of one big, fragile brain, what if we could spread the intelligence all across the factory floor? And that question led straight to the rise of the distributed control system.
And this right here is the game-changing shift. We move from that high-risk, centralized DDC model to a distributed one. A DCS doesn't have one big brain. It has a whole network of smaller, dedicated microprocessors. Each one handles its own little part of the plant. They all talk to each other, sure, but they can all think for themselves.
Now, this is what makes a DCS so incredibly powerful. It does something called real-time processing. See, your laptop at home, it runs a program and then it stops. A DCS controller is in a constant loop. It is always sampling data, rerunning calculations, and making tiny adjustments hundreds, maybe thousands of times a second. It literally never stops working. And the benefits of this were just enormous. The system could now grow, you just plug in more modules as you need them, and crucially, it had fault isolation. If one little module failed, the rest of the plant just kept on running. Maintenance got way easier, and the overall control was just far, far superior.
But hey, the evolution didn't stop there. The next huge leap forward was all about making the entire factory digital, from the tiniest sensor all the way up to the main control room. This was the Fieldbus revolution.
This table really shows the next massive jump. A DCS was kinda semi-distributed and semi-digital. It still needed a ton of special cards to convert analog signals to digital. But a Fieldbus Control System, or FCS, is fully distributed. The control logic isn't sitting in a rack of cards anymore. It's built right into the smart devices out in the field, and the signal is pure digital, from end to end.
This all-digital approach brought some pretty amazing advantages. I mean, by getting rid of mountains of wiring and specialized hardware, the initial cost drops like a rock. And because everything's digital, you get these incredible diagnostics. A smart valve can now send a message to the control room saying, "Hey, I think my sensor's about to fail," long before it actually becomes a real problem.
So we've seen how the technology evolved, but here's the thing. Whether it's an old DDC, a DCS, or a modern FCS, actually building one of these systems follows a universal, highly structured process.
And this is a super meticulous process, Nothing is left to chance. It all starts with really deep analysis and design, way before a single part is even ordered. Then comes the tough work of installation, followed by this critical tuning phase where engineers make sure every single response is perfect. And finally, everything, and I mean everything, gets documented, creating a perfect blueprint of the factory's nervous system.
But look, no system is perfect. Things are gonna go wrong. And that's why a huge part of any control system is its alarm philosophy, basically how it gets a human's attention. So when a new fault happens, the system immediately tries to grab your focus with a blinking light and some kind of audible alarm.
Now, once an operator sees that alarm and hits the acknowledge button, the system changes. The annoying sound stops and that blinking light goes to a solid, steady light. This basically tells everyone on the floor, okay, we see the problem, but just so you know, it isn't fixed yet.
And finally, once the technicians have gone out and actually corrected the issue, the fault gets cleared in the system. That steady light turns off, signaling that everything is back to normal. The board is clear.
And every single one of those alarms, every action, every variable, it all gets logged. You see, these systems aren't just for control. They are massive data-generating machines. And all that historical data is absolutely vital for analyzing performance, boosting efficiency, and for figuring out exactly what happened when things went sideways.
So when you step back and look at it, this whole journey is a really clear evolutionary path. We went from a single, fragile, central brain that could easily get overwhelmed to this distributed, resilient, and deeply interconnected nervous system that can handle incredible complexity without even breaking a sweat.
And that kind of brings us to our final thought. With things like AI, cloud computing, and the industrial Internet of Things all coming into play, these nervous systems are getting even smarter. So the real question is, what comes next? What will the brain of the factory of the future really be capable of?